Hey, this is Dr. Rob. Welcome to Biblical Genetics. Hey, if you've been paying attention to my channel or to creation.com, the articles I've been writing, you probably have noticed that there's a bit of contention about how long ago Eve lived. Now, I, of course, don't think she lived hundreds of thousands of years ago. I think she's a biblical Eve, who lived a few thousand years ago. The last episode I published on this topic was about 6 months ago. And I was somewhere in Colorado looking at these sand dunes. Well, Creation Myths came out with a video right after that, basically saying I was wrong. And the reason is because natural selection happens in mitochondria. Therefore, you can't, Carter, look at the mutation rate today and know what the long-term mutation rate is, because selection is going to be removing a lot of those mutations. Game on. Now, I'm going to be walking as I do this. I decided to come out for a hike, and they have this beautiful new park that connects a beautiful new trail that connects one park to another near my town. At the other end, I filmed, I think, 3 episodes of Biblical Genetics, but this end, I've never done. In fact, I've never even been on this brand new trail. So we're going to start off at the ballpark, which is my introduction to the topic, and then we're going to take a lot of twists and a lot of turns along the way, which is the other part of my topic. Now, the light sensor in my camera is going to be going bonkers as I go between shadow and sunlight, but we'll take care of that maybe in post. Maybe you people listening on podcasts, you don't have to worry about that, so that's okay. Now, my article just came out. When did Eve live? It's getting a lot of traction, getting a lot of comments. I worked really hard on that. Now, it did take me months to produce it because I've been really busy. I just finished up a book. Very excited about this. My book should be out by the end of 2025, maybe early 2026. And yes, you will be definitely a prize of that when it's ready. I'm excited. And my boss gave me permission to start my next book. I've got over 50 pages of notes, a really cool outline, and that's going to be another amazing work, I believe, anyway. So I'm busy. I've also been traveling a lot. Since my last video, I've been to Colorado twice, Arizona 3 times, the DC area, Kentucky, Tennessee, Carolinas, Florida. I'm going to Maryland again next weekend. They've got me hopping. Back in 1981, some scientists were looking at human mitochondria. We didn't have the ability to fully sequence mitochondria yet. No. All we could do then was take enzymes, bacterial enzymes, called restriction endonucleases, that would cut DNA at very specific locations. Almost all of them cut at palindromes. So the forward and reverse sequence are the same, and usually 6 or 8 letters. So Echo R1 is the most famous one. Yeah, I'm supposed to remember what the palindromic sequence is, but for a moment I forget. But the forward and reverse sequence are the same. And when you have enough of those, you can cut DNA at a lot of different places. In fact, the first sequencing for mitochondria was based on chopping up the mitochondria, running the DNA out in a gel and seeing what pieces form, how long the pieces are, and then trying to figure out where the cut happened. And they spent a lot of work doing that. But in that early work, they're mainly dealing with just the control region. The mitochondrial genome is a circle. There's some genes in it, mostly RNA genes, some protein coding genes. But at the beginning and the end of that circle, at least where we chose the arbitrary starting point, it's actually not arbitrary. It's the start of replication. It's where the mitochondria, when it's copied, the starting point is in the middle of what's called the control region. That was the basis of the first mitochondrial Eve. Yes, they looked at it, they chopped it up into pieces, they started sequencing pieces, and they said, oh, look at that. When we put these into a phylogenetic tree, an evolutionary tree, we have this African branch that's outside all of the other branches. Therefore, the ancestor must have lived in Africa. Oof. Don't agree, especially because I don't agree that you can use a molecular clock to put dates on those branches. It's not necessarily true that just because this African branch is longer, that it's older. Okay, so that's another story. But that's where it came from, 1981. By the time 1988 came around, we knew already that the mutation rate was fast enough that Eve would be put in the biblical time frame. mean, Carl Wieland wrote an article in Journal Creation, it's now on creation.com, called The Shrinking Date for Eve. Well, yeah, when you look at the mutation rates, it doesn't take long to get a mitochondrial Eve that equals the biblical Eve. When we look at all the mutations of the mitochondria in the world, the big family tree, and count up the rate that we can see mutations happening today, it will only take a few thousand years to account for all those mutations. Therefore, Eve was young. Oh, no. That caused a raging contention. One of my sources said it promoted an intense debate. Oh, yes, an intense debate. How can we account for this fast mutation rate that we can measure? But the evolutionists would be saying, well, we don't believe Eve lived only 6,000 years ago. No way. She lived, 200, 300,000 years ago. We have to slow down the mutation rate. And there are ways to do that. And so my article on creation.com, When Did Eve Live? I sought to comprehensively list all the things that affect the mutation rate, that slow down the accumulation of mutations, trying to be, fair to the evolutionary model. I did my best. Now, I might have missed something. Fine. If you find it, great. I know as soon as I posted that article, some people wrote back about typos, so I think we got the typos fixed now. Forgive me, I am human. But when you have an article that's been edited so heavily, that's the type of article where you get a lot of typos because this is what happens. Okay, so I'm a human. I make mistakes. My mistakes are just like mutations. Oh, but because I'm human and I'm smart and I have the ability to edit, I can fix my mistakes, unlike biology, which has a problem fixing mistakes. That's why we get mutations. All right, stupid illustration, but just popped in my brain. So one way that they explained this single human female ancestor, which was a bit of a shock, was not predicted. It was folded into evolutionary theory by invoking a bottleneck. Now, the bottleneck has other things later on that they also use to support it, but this is the first idea of the bottleneck that I'm aware of, was trying to explain mitochondrial Eve. Now, Eve, let's say it this way. If humanity went through a very small population size at some point in the past, well, in small populations, you lose a lot of genetic diversity. I think that's probably pretty easy to understand. Only a few people, you can't have a lot of genetics in just a few people. You're going to lose genetic diversity. The smaller the population, the more profound that loss is and the faster it happens. So if you had just a few thousand individuals over a very long time, and that's the key, a very long time, I don't know, 100,000 years or something, then eventually you're going to lose all the mitochondrial diversity except one, because someone has to be the mother. But if you have a small enough population, eventually, mathematically, it is true, you will arrive at a mitochondrial Eve. Even though the population started out with a bunch of women, eventually only one will win. And she'll be the ancestress of all living people from that point forward. So their Eve is not our Eve. Their Eve is a mathematical construct. Ours is a historical reality. So that's where the bottleneck came from. But it's really interesting because they expected to find many mitochondrial sequences in humans. In fact, it was allowable that we would share mitochondria with chimpanzees. Actually, back then, chimpanzees was not guaranteed to be the ancestor. People were still debating that. But we could share mitochondria with chimpanzees, theoretically. And if that was true, there might be some people who are more similar genetically to chimpanzees than they are to other people. That is not excluded by evolutionary theory. I'm praising God that that did not happen, because I think the racist implications of that would be tremendous and the sociological implications would be extremely difficult, but that didn't happen. They kind of expected many. They found one. For the biblicalist, I guess I can call myself that, for the person who believes in historicity of Genesis, we can have one Eve, kind of expect one, but we could have more, because it all depends on how many mitochondria God put into Eve's egg cells. he wasn't limited to just one. He could have a different mitochondrial strain in every one of her millions of egg cells. Oh. So, the amount of diversity today would depend upon how many children Eve had, how many daughters Eve had, and then how closely related the three daughters-in-law of Noah were to each other. If they were very distantly related, they could either have had two options. One, different mitochondria from Eve, or two, mutations could have picked up in that 1600 years between Eve and the flood. There could have been up to 3 different mitochondrial lines. But I no longer say there was 3 lines. I said that earlier in my career, my creationist career. But no, because what if 2 of the girls were sisters? Well, then they would have the same mitochondria, and then there would only be 2 mitochondria. What if all 3 of them were sisters? Well, then there's only 1 mitochondria. Mitochondrial Eve was their mother. And all of the mutations we see today are post-flood. So we have a lot of different options. It's really kind of fun to explore all those things. But what it means is that they expected a few, they got 1. We expected 1, we could allow for a few, and everyone got 1. So it kind of fits both theories. We predicted that it should be true, it doesn't have to be. They predicted it wouldn't be true, but it could be. Just a little funny little anecdote there also. But because both sides can accept the data, therefore the timing is critical. The timing of Eve is 100% the argument. How do we put a date on Eve? Or if you like, how do we date Eve? Even though she's dead, you can't date her. But in order to do this, I created a new phylogenetic tree. I'm going to have to do a whole episode on how I made that tree. I went to GenBank and I downloaded every single available human mitochondria. And then I noticed that some of them were from cancer cell lines. I had to parse those out. I noticed some of those were from ancient DNA. I had to remove those also, because ancient DNA always has extra mutations that don't belong. So I got rid of all that, and I started with like 56,000. Ended up with 30-something thousand. And I lined them up using a very laborious process. It took me weeks. And then I filtered them because I didn't want a bunch of people close related. I wanted to see the main branches on the family tree. So I said, okay, I'm going to compare every sequence to every other sequence. And if any sequence is less than 50 mutations apart from another, I deleted the second one. And I ended up with this beautiful tree, which you see in my article. I'll be showing it on screen about now, but if you're in podcast world, you can find it on the website or on my article on creation.com. Okay. So I've made this beautiful tree. And now I've got a pretty good indication of the major branches of the human mitochondrial family tree. Now, the evolutionary Eve is on an African branch. The biggest reason for that, that's the halfway point between the extremes. But because those African-only branches are a little longer than the others, that means that the middle of the tree is not the middle of radiation of all people. It's actually on an African branch. That's where the African Eve idea comes from. Now, because I reject a molecular clock, I don't think that you can just place Eve there. So for the creationist side, where do we place Eve? I don't know. It could be anywhere on the tree, but it's more likely to be near the center than really close to a living person today. So the closer to the center you are, the more likely that's where Eve would have been. But I can't put my finger on it. It could be the location, could be anywhere within some statistical window of probability. I'm sorry, I would love to say, this is Eve's sequence, but I can't do that. Now, I did publish the sequence of Eve's mitochondria, about 15 years ago. Eve 1.0. And some evolutionist afterwards, a well-known guy, commented on that paper in another paper that they published. It said that I misunderstood what a consensus sequence was, and the consensus is not the ancestral sequence, even though in the paper I quite clearly specified the difference. Whatever. And he said, this leads towards creationism. in this, secular paper. He wrote that and referenced my article in the ICC, the International Consecrationism, I published after I published this, what we call secular paper. So they're on to us. They know it. But I do know what's going on, at least in that respect. So here's the deal. We've got a mutation rate we can measure, and we have a long-term accumulation rate, and they're not the same thing. The long-term rate should be a little bit lower than the rate we can measure for multiple reasons. But when we measure it, when we look at family trees, we know how many generations or how much time has separated two people, we get a whole range of measurements. The earlier ones were really high. Earlier ones were just on the control region, was like 1 to 1.5 mutations per generation. Woo! Those haven't held up very well. And now that we have full genome sequencing and millions upon millions of mitochondria that are available to DNA testing companies and things like that, and a lot of family studies have been done with known family trees, our mutation rate, 0.03. That's one mutation every 30 generations. And it ranges up to, I found, up to 1.5, but most of the modern ones are about, 0.05, 0.7, things like that. So it's less than one mutation per generation, which is fine for now. Just hold on to that. That does mean that Eve didn't live 6,000 years ago. Those slow rates are too slow for me, but they're still too fast for the evolutionist. That's really funny. None of us like the number. Eve should have lived less time ago than those really low mutation rates would indicate. But for the evolutionist, if you take those low mutation rates, then Eve was not 200,000 years ago. She's less than that. So, all this, as I said earlier, promoted an intense debate. Now, in my article, I listed 6 different ways that the mutation rate can slow down. That is, the long-term rate of mutation accumulation should be less than what we can measure. Now, I do have an issue in that some of the best measurements are done on very homogeneous populations. Like one of the most famous one done on Iceland. I don't think that modern Icelanders, who are very homogeneous, are necessarily a good proxy for all people who've ever lived everywhere on Earth under a range of different environmental conditions and a range of different genetic conditions, because we know some families have defective DNA repair enzymes. We know that. And when they have children, their children have more mutations than other people do. That exists. Those things exist in the modern human population. And if you had that happen in a very small population, which is likely, then you're going to get a lot of mutation in that population very quickly. And it's not necessarily true that the modern population will have a fast mutation rate, because that defective DNA repair system may have been lost. Especially, it could have been lost through drift, or if they merged with a larger population, again, it could have been lost through drift, random chance, or natural selection could have killed it off too. So, all these different ways to affect that mutation rate. But here's my 6 points. Point number 1, selection. This is creation myth, big argument. He basically said that this proves Carter wrong, whatever he actually said. It's been a long time since I watched that video, but he thinks that this proves me wrong. And yet, there's multiple problems with this. First of all, mathematically, I'm the one who ran the calculations. I ran a lot of simulations to try to figure out the difference between the mutation rate and the accumulation rate using a population model. My own population software indicates that, you can remove some, but not many. You can only remove a fraction without killing off your population, or basically most mutations are nearly neutral. Everyone believes that. Therefore, you can't remove most mutations. If you wanted to remove a mutation, it has to be selectable. It has to rise above the noise. the environmental noise, the background genetics noise. It has to have an effect on the individual. You, right now, you as a person, you're carrying mitochondrial mutations that your ancestors did not have. Do you feel like a mutant? Probably not. Are you being naturally selected away? Probably not. In fact, yeah, there is a whole lot of selection in the mitochondrial genome. I looked at all these lined up sequences and I calculated about half of the mitochondrial genome is invariant. And that can mean one of two things. Either it's not very old. There's a truck coming up the road here. Either it's not very old and we haven't had a long time for mutations to accumulate, or more likely, there are a lot of mitochondrial mutations. Does this guy go by? There are a lot of mitochondrial mutations that are deadly, that are instantly removed from the population. Yeah, that's definitely true. And truck's gonna line up again. I started this walk early this morning, and it rained really hard last night, and I was kind of hoping that there'd be a cold front, and it's supposed to be cloudy this morning. It dawned bright and clear and super humid. This is the end of September, man. I'm waiting for fall temperatures, and it's not. So I have too many clothes on right now, so I'm sweating, and I started before the maintenance guys were up, but now they're up, and they're driving away, so I think they're far enough away I can talk again. Yeah, it's probably quiet. All right, so selection. Yes, it happens. Most people walking around have mutations in their mitochondria, but they're not being selected for or away because they feel just fine. Yes, there are a lot of mutations that do not appear in mitochondria because they're lethal to the embryo, maybe to the cell, or maybe to the child. Or, and here's the kicker, people with selectable mitochondrial mutations don't appear in phylogenetic or in family tree studies. When you say, hey, I want to participate in this study, or a scientist says, hey, would you like to participate in our long-term mutation accumulation study of mitochondria? One of the questionnaire is, do you have a mitochondrial disease? And this person says, why, yes. They'd be like, all right, you can't participate in our study. Yeah, those people in other types of studies, the mitochondrial disease studies, not the normal people studies. So there's a bias here. If you're going to claim the mutation rate we can see in families, that you have to apply natural selection to that, it doesn't work. Because one, the selection has already happened in the embryo, or in utero, in the embryo, or as a child, or you have something that's actually affecting you, you're not allowed to participate. So Teration Miss is completely wrong on that. Plus, mathematically and computationally, you can't reduce that many mutations. You can't remove them without driving your population extinct. So selection doesn't work. All right, the second thing, very similar, is genetic drift. When you have a small population, you're going to have mutations occurring, but because of random chance, it just might happen that that mutation becomes very common in the next generation. Just random chance. And in large populations, genetic drift doesn't happen. When you get above a few thousand people, it slows to a crawl. When you have less than a few hundred people, it's very fast. And there's a transition there. It's a pretty fast transition. According to all the population modeling I've done, it really, it almost completely stops. But it is there. And if you have enough time, hundreds of thousands of years, for example, you will get a little bit of genetic drift. But drift tends to randomly remove new mutations. Because the more rare a mutation is, the more likely it is to be not passed on to the next generation. Does that make sense? The more rare a mutation is, the less likely it is to be passed on to the next generation. Because some people don't have any children, or some people don't have any girls. So rare mutations are constantly being deleted from the population. Now think about this. Every time you have a mutation in the mitochondria, it is by definition the most rare mutation in the world. It occurs in one person. The frequency in the modern population is 1 over 8 billion. That's a very, very low frequency. And all those mutations are very likely to disappear. And something like 99.9999 something percent of them will disappear. So is that the reason why you can't use the short-term mutation rate to estimate the long-term mutation rate? Because most of those mutations will be removed? No, not even close. Because yeah, most mutations are removed, fine, but a lot of mutations happen. Let's say that the mutation rate is as low as 1 every 100 generations. Well, there's 8 billion people, there's 4 billion females, that's 400 million, it's 40 million new mutations just in this generation. Let's say that, I don't know, if only one out of every 1,000 survives. Well, you think divided by 1,000, you're talking like more mutations have appeared in this generation alone than the size of the mitochondrial genome. Every single possible mutation has appeared in this generation, and those are the ones that are not going to be lost to drift. Those are the ones that are not going to be selected away. Those are the ones that are going to stick. So drift doesn't matter. You have a high likelihood of any mutation being lost, but you have a lot of mutations, and those two things balance out. In fact, something I learned in my population genetics class in my PhD work, the mutation rate equals the fixation rate. That is, if the likelihood of mutation not being lost is proportional to its frequency, if you multiply that times the mutation rate, you get the number of mutations that are not lost. If they're not lost, they become what's called fixed. That is, there is a set difference between humans and chimpanzees. The entire human population becomes one letter different from chimpanzees every time a letter becomes fixed. And the fixation rate approximates the mutation rate. They know this. It's in the textbooks. I have the mathematics in my article. In fact, a couple of articles have had the mathematics. One person complained that I'm inappropriately using the statistics, but I explained why it does work and why they know it works, and it all works out just beautifully. Mutation rate approximates fixation rate. So drift doesn't apply. So selection doesn't work, even though it slows down a little bit. Drift does not work at all. The next one, the third point I made was that, half of the mutations in these family studies occur in males. And those don't count. So at best, we can divide the mutation rate by 2 and take only half the mutation rate. That's not quite true, because if you're only looking at like parent to child, half of the mutations are going to be in males. But when you have a long family tree, many generations, well, it's only the terminal individuals that are males, and that's only a small fraction of the total number of people in the study, because you've got their mother, their grandmother, great-grandmother, great-great-grandmother, and the mutation happens somewhere in that line, not just in the male. So that male sister is going to carry it. His female cousins are going to carry it on the mother side. So you can't just divide by 2, but it is a little bit. And when you account for that, the long-term accumulation rate will be a little bit lower than the short-term mutation rate. So selection in factor into males does have a little bit of an effect. The next point, number 4, something called heteroplasmy. Now, I know you've been listening to me a long time. I just threw in a big word. You're probably tired of listening to me, but heteroplasmy. Follow this. When a mitochondrial mutation occurs, it doesn't instantly replace all the mitochondria in the cell. Most cells have about 1,000 mitochondria. Now, it takes time for that mutation to build up in a cell line. Therefore, a female can often pass more than one mitochondria to her child. This happened in when they dug up Tsar Nicholas II. In fact, one of my first ever biblical genetics episodes, I was at Red Rocks Park in Colorado, which I've been to twice since my last episode now. But Red Rocks Park, and I talked about Tsar Nicholas II. When they found him after the after communism collapsed in Russia, they dug up his body near Ekaterinburg, and they found 2 different mitochondrial strains in it. And I said, oh no, do we have the remains of 2 different people? No, because they also went and exhumed his brother, who was buried in a crypt in Moscow, and his brother had the same 2 mitochondrial strains, meaning their mother had 2 different mitochondria, and she passed different proportions to each son. One had more of one had more of the other. But over time, that passing from one generation to the next, the mitochondrial frequencies of the different lines, they fluctuate wildly. It all depends upon how many mitochondria are passed to the next generation. Some estimates are as few as 3. If you're only taking a random sampling of 3 out of an egg cell or a primogeniture cell with maybe 1,000, and it's like 50% of one and 50% of the other, there's a pretty good likelihood that you're going to get all of one. And all of a sudden, every descendant from then has this other type of mitochondria, one of the mutant mitochondria. So we have genetic drift happening in the egg cells profoundly. Human population never got down to 3 people after it formed, got down to 8 people, but it never got down that small. Therefore, genetic drift is a very strong factor in development of eggs. Ooh. But see, we're not removing a lot of mutations that way, because that's in the egg, and all the studies are done in adults. The drift has already happened. The selection has already happened by the time we get to adults. So that's heteroplasmy. A person can have more than one cell. The next thing I talked about, number 5, was the fact that the somatic, that's the body tissues, often have a lot more mutations than the reproductive cells. Yeah, egg cells are protected. They don't divide. They don't mutate nearly as fast as like skin cells. I mean, I'm over 50 years old. I probably got 60,000 mutations in every one of my skin cells. That's not good. That means that my body's falling apart. It's driving towards cancer. It's driving towards loss of elasticity. All sorts of problems happen as your cells divide. But your gonad cells, trying not to use too many big words here, don't divide nearly as fast, at least for the eggs. Therefore, the mutation rate is lower. So if you take a spit sample or a blood sample and you use that to measure the mitochondria, to sequence the mitochondria, there's probably some differences between that and the gonads. Therefore, you can't use, one might try to claim, the mutation rate from those studies as an estimate of the real mutation rate, because it should be higher, except one thing. That is that usually that causes heteroplasmy. Yeah, so if you find that, oh, these cells have this mutation in it, but these other ones don't, you have a difference there, and the heteroplasmy can be accounted for and removed. So that's not really a factor. And the last one is that most of the mutations, and this is true, most of the mutations happen at what are called hypervariable sites. There are places where the DNA polymerases hiccup. They just hiccup. They're going along and they have C's, 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 usually a C's, and it might add an extra C or delete a couple C's, and it happens, and it's crazy, and it's difficult, and it causes geneticists to I don't know, be very frustrated and pull out their hair. I have run into these in mitochondria. I've run into them in H1N1 influenza virus. I've run into these in the COVID-19 virus. I've run into these in Ebola. All these different groups of viruses, I've taken many sequences and aligned them. And it was really hard. And these places with variable numbers of C, sometimes variable numbers of AT, are really difficult to deal with. But at least one published paper said that even though most mutations happen at hypervariable sites, they do not affect the long-term mutation rate. Okay, so I can just take that and say, even the evolutionists are saying it doesn't matter. But the problem here is that because it's hypervariable, the mutations can be erased. You can add some Cs, you can remove some Cs. So if you're using that to estimate the mutation rate in family trees, you're going to have an overestimate. And it does need to be accounted for, but one person said it doesn't even matter. And I'm going to say, yeah, it matters a little bit. A little bit. So there's actually 3 things there. Selection removes some of the mutations. Drift does not. The fact that half the mutations occur in males, you have to account for that. That will reduce it a little bit. Heteroplasmy doesn't count. Somatic versus inheritable cell lines don't count because it's more heteroplasmy, but you do get a little bit of mutations at hypervariable sites that will have in some effect. Okay. Yeah, so now I'm at the twisty-turny part of the trail. Perfect timing, because I'm also getting to a different part in my article and in my presentation to you. You might be thinking that this doesn't go anywhere. Yeah, that's true. You might be thinking that all I'm doing is talking about theory. Yeah, that's true. And assumptions. Yeah, that's true. The conclusions are based on assumptions and theory. I have every reason to question the assumptions. I have every reason to think the assumptions aren't true, and I don't believe the theory. So what am I to do? How do I then explain how long ago Eve lived? Well, I said earlier, the mutation rate is a little too slow for me. But I also said that I don't think that necessarily modern people are a good proxy for all people who have ever lived across the whole world under all environmental or genetic conditions. Okay? And in the Bible, we have something that is profound, something that should have an amazingly huge effect on mutation accumulation rates, and that is lifespans. Old people give more mutations to their children than young people. We can measure that. That has been measured extensively. There is a mutation burden with the age of the parents. We know this. But none of those are done on people who live for biblical lifespans, because no one today is living a biblical lifespan. But something I've talked about, I've done an episode on this show. I have an article on creation.com, which is in the Journal of Creation, called Patriarchal Drive. That's the idea that the patriarchs after the flood, because they were old when they're having children, they're going to produce children with massive mutation loads. But one patriarch might have a child earlier in life with a low mutation load, but a couple hundred years later, if you have another child, that child is going to have a fantastically huge number of mutations. Therefore, there's no molecular clock. Therefore, we should expect from first principles in the biblical model a period of time where mutation rates were much faster than today. That's what I'm getting at. Patriarchal drive. And then the other question is, from the biblical model, actually, I think I said this a little bit earlier. I've been talking a long time now, but a little bit earlier. Where do we place Eve? Well, we could put her at the midpoint of the tree, which is on an African-only branch. I don't believe that. I don't have no reason to put it there. We could put her at the center of like diversity, where the most number of branches are. That might be location. Maybe we want to find a three-way split. The problem is there aren't any three-way splits in the tree. Now, if I cross my eyes and cross my fingers and, look at it upside down and backwards, I might be able to find a place. Yeah, I think there's a three-way split there. But it's not really true. Anytime you have a major branch, there's a three-way split there. You have something leading to the branch, and one branch goes left and the other branch goes right. That's a three-way junction. Any one of those could be the location of Eve. And there is a lot of them towards the center of the tree. But as I said earlier, there might have only been one mitochondria on the ark. So we might be talking about every single mutation we see is post-flood. In fact, a lot of the people spreading out on the planet after the flood might have had identical mitochondria. So all of the differences we see are branches that formed more recently, and in which case there wouldn't be a three-way split. One of my Facebook commenters, I don't remember the exact phrase he used, but he basically said, man, the evolution has been treating this like a done deal, and it ain't so. And that's true. It's not so. It's not like we have the answer, therefore the Bible's wrong. Not at all. Take confidence in that. It is not true. The Bible's wrong because they have the answer. The answer depends upon theory. The answer depends upon, therefore, philosophy. The answer depends upon assumptions. And the answer, when you look at it scientifically, all the assumptions are questionable. The philosophy is based on a version of history I disagree with, based on a philosophy I disagree with, naturalism. It's the whole thing is couched in terms of non-finite, non-certain categories with loosey-goosey stuff everywhere. So because of that, I feel perfectly comfortable saying, no, I don't believe that. I think Eve was recent, and here's all the evidence for it. Here's the reasons why I believe that. Here's the things that back it up. And I'm looking at the evolutionary assumptions, and I can question every single one of them. Therefore, Eve could easily have lived 6,000 years ago. There's no scientific proof either way. You got that? You can't use science to know when Eve lived because there are too many variables. You can know that she lived a short time ago because of the mutation rate. You can know that there are a few ways to slow down the mutation rate, but they're not enough to get her to 200,000 years ago. And that's all. That's the answer. Now, this is frustrating. I wanted a very succinct, pat answer, and I didn't find it. And that's the nature of science. Science very rarely gives us very concrete answers. There's so many unknowns and so many assumptions and so many people making mistakes as they're trying to, logically analyze things. And you have bigotry and bias because humans are like that. That's human nature. Oh yeah, this bridge. I filmed a video on this bridge at one point. I filmed another one over there, and I filmed another one over there. This was my favorite park. I said that in one of my videos. My favorite place to film. Oh, this is really pretty. What a beautiful day. Hey, it is a beautiful day. Christian, take heart. We got God on our side. There's the Bible on our side. Science is on our side. Science does not say that Eve is not biblical. Science is saying, yeah, Eve was probably biblical. And the Bible says Eve is biblical. So I'm taking the Bible at face value. I'm looking at science and saying it's not contradicting me. And there are valid reasons for thinking that Eve in science is the Eve of the Bible. I've been rambling on for 45 minutes now. Have a wonderful day. If you'd like to help support my efforts on biblical genetics, there'll be some links in the show notes. Please go to creation.com and read my article. If you want to, you can go look at all the links. I'll probably have at least one of Creation Myths videos link there, just so for your own reference, so you can see what he said. I just did not have the heart of doing a point-by-point rebuttal of that because I didn't need to. It took me 45 minutes actually to go through all the details, all the things that he missed. So that's all for me for today. Be blessed, be strong, be encouraged that the Bible is true.